series, the functions we can use for Fourier series relatively limited. Yeah, so here, let me compare the functions. So the functions we need to work in the real world. Yeah. We can consider these two types. The first type defined on finite interval, AB. So it's a finite interval. Yeah. Second, defined on infinite interval. Yeah, infinite interval, like this. Okay, yeah. Or there is, infinite interval, there is a one-sided infinite interval case. Yeah. One-sided from negative infinity to 0 and from 0 to positive infinity. One-sided, yeah, infinite interval. All right. But most of the time we consider the, the whole real axis. Yeah. So in these two cases, yeah, in the finite interval, yeah, then all the functions defined in finite intervals, if they satisfy a certain condition, yeah, we need some condition. Then we can use Fourier series. We can use Fourier series to represent those functions. Yeah. Then on infinite interval, then this case, we need divide it into another level. Yeah. First level, periodic function. Periodic function, the first type. Although defined on the whole real axis, but these functions are special functions. They have this property, periodic property. Yeah. The second, non-periodic. Right? Yeah. Then the periodic function, then we can still represent by Fourier series. Fourier series. But non-periodic, yeah, cannot. Yeah. So for this last case, still there are large number of functions. They belong to this category. Yeah. Non-periodic functions defined on the whole real axis. Yeah. So we cannot represent these functions as Fourier series. Yeah. So for that reason, we need to consider a different way to represent these functions. So we don't want to, miss or skip this big class of functions. Yeah. All right. Yeah. So a new method is really needed to represent this large class of functions. Yeah. All right. For that reason, yeah. So we move to this topic. Fourier integral. Yeah. All right. But when we move to Fourier integral, all right. Yeah. All right. So last time we did some calculation. Yeah. Here, let me explain a little more on this calculation. Yeah. The last time, the annotation I drew, I cannot erase. Yeah. I mean, the PowerPoint slides does not allow me to erase my annotation I did last time. Yeah. All right. First, when we start, so given a function, so here, how do we, so our goal, remember our goal, yeah, so let me write the goal clearly here. Yeah. Given a function f of x defined on the whole real axis from negative infinity to positive infinity. Yeah. Now we want to represent this function using some way similar to the Fourier series expansion. That's the idea. Yeah. At the beginning, we may not know how to represent it, right? At the beginning, we do not know. Yeah. Yeah. We have the experience with the Fourier series. So when we start, we want to start with the Fourier series. Okay? All right. But the question is, this function, so here we assume this function is non-periodic. We assume this function non-periodic. That means we cannot calculate its Fourier series expansion. We cannot do that. Right? Yeah. But we have to find a way, we have to do something, right? Yeah. So here we have to find a way to represent this function. Yeah. So here we need to find a way. Yeah. But the knowledge we have at this point is the Fourier series representation. That's the knowledge we have. Okay? Other than that, we do not have other knowledge. Yeah. All right. So the question becomes, how do we use the Fourier series representation to approximate this function? Yeah. So here we want to approximate this function with the Fourier series. That's very natural, right? Yeah. That's very natural. All right. Then we need to think about how to approximate this function. The approximation idea. How to approximate this function. We need to find the approximation way. Okay? All right. So here, there is a simple way to approximate this function. Yeah. So let me draw a graph here. Draw a graph. Yeah. Yeah. First, let's draw this f of x graph. Yeah. Let me just, like that. Okay. This function is defined on the whole real axis. Yeah. All right. Yeah, because you cannot apply Fourier expansion on this function directly. Yeah. Can we do some special operation on this function so that we can apply the Fourier series expansion? That's the question. Okay? We do some special operation on this function. Yeah. If we do that, then we can do the Fourier series expansion. Yeah. Yeah. The answer is yes, we can do that. Now we do want some special work. So what's the special work? All right. We truncate this function, left-hand side, right-hand side, at some location, left hand side negative L point, right hand side at x equals L point. This L, some positive number, we can change. Yeah, we can change that function. So here we truncate. So we introduce a new function we call FL function of x. This FL function only take the portion of the original function between negative L and a positive L, and other than that it takes 0. Okay, outside this interval it takes 0. Can we use this way to approximate an original function? Yeah. So within this interval, these two functions have the same value, but outside this interval, they have different values. Yeah. But the question is, let's represent this function because we know we can use Fourier series for these functions, right? Yeah. So now it's legal to represent these functions by its Fourier series. It's legal, okay? Yeah. But after that, the question, can we make this L goes to infinity? Yeah, because that L is a positive number, we can make it larger and larger and push it to infinity. When we push this capital L to infinity, then it covers this FL function approximates the original function extremely well, right? Yeah? Yeah. So use this idea. In this way, we can use the Fourier series expansion on this FL, but after we get the formula, then we make this L goes to infinity. How about that? That idea. Okay? Yeah. So this kind of details I didn't give you in the last class because at that time we do not have enough time. We had only 10 minutes in last time, so I couldn't expand this much. Yeah. Now, based on this understanding, now we understand the calculation here. Yeah. So it's a little better to understand. Okay. All right. So then we work on this FL function, and when we work, yeah, we can do the Fourier series expansion. So we get this formula. Yeah, FL. Yeah, that's legal. Okay. Yeah, and we assume this function is good enough to have its Fourier series expansion. Yeah. And the same. Okay. Yeah. At this point, we write it the same. Yeah. Yeah. All right. Then we know how to calculate the coefficients A0, these AN, BN coefficients. We have the formula. Now we just apply these formulas here. Apply A0 formula. Yeah. So we get first term. Then we apply other formulas. Yeah. AN formula, right? Yeah. And so here the notation. So if some of you, yeah, because what here, although we use the Wn equals n pi over L, but here you see this delta W. Yeah. So that's the new notation. Yeah. Delta W is just the pi over L. Pi over L. Yeah. Yeah. The small unit pi over L. Yeah. Yeah. So each W, you can see just a multiple of this delta W. Okay, n multiple. Yeah. N multiple of this delta W. Yeah. All right. So then, because apply the formula, yeah. Because when you apply the formula, you can do the conversion. Yeah. Because apply the formula, we need to take the 1 over L out. 1 over L equals 1 over pi times delta W. because delta W pi over L. Yeah. So that's the reason 1 over L in the original formula is replaced by 1 over pi times delta. So 1 over pi, we factor it out. That's why inside you see the delta W. Okay? Yeah. So for other parts, we just copy. We copy the formula. So you get that. All right. Then, all right, so this formula, we know it's correct, right? Yeah. We apply our old knowledge here, so no problem. Okay? Yeah. So we just carefully, check the coefficients, some variable. Yeah. Yeah. All right. After that, then the important step, we make L, capital L, goes to infinity. This time we do that limit step, okay? That capital L larger, and goes to infinity. When we do that, we need to take the limit, right? Yeah. So let's look at the limit of the first term. The first term, first we need to assume in our original function, we need a condition. So the absolute value, the integral of this absolute value from negative infinity to infinity must be finite number. Yeah. So we call this f function must be an integral function. Integrable function. Yeah. Yeah. Because if we have this condition, then the first term is well defined. The first term can be calculated. Yeah. So it's a part of the integral in the original function. The first function, the integral term has some finite value. Yeah. Based on the integrable assumption. The first term has the finite value, but you have the numerator you have finite value, the denominator L goes to infinity, so the whole term goes to 0. Okay? After you take the limit, when you push L to infinity, the first term goes to 0. It's gone. Okay? You cannot see it. Yeah, you cannot see it. Yeah. All right. Then the remaining part, we have two summations, right? The first summation on cosine related terms. The second summation on sine related terms. Yeah. All right. Then we need to introduce a new variable. Yeah. Yeah. All right. Because here we have first we have integral. So this integral we use the v as the variable. Integral. Yeah. Then this w another variable, w, yeah? W is a summation. Remember, when we define integrals, we can use a summation to define integrals, right? Yeah. So here you can see the summation and the integral closely related. Yeah. So we use the summation representation for the integral. Yeah. All right. So when we do that, yeah, this delta w becomes dw, right? Yeah, because when you make the L goes to infinity, that delta w becomes smaller and smaller. Yeah, the delta w pi over L becomes smaller and smaller. So we use this very small quantity differential dw to represent that, that small quantity. Yeah. dw. Yeah. So then Wn x, Wn, so this Wn, yeah. N, yeah, Wn x. Remember this n is a variable, right? The n variable change. Yeah. Wn x, yeah. So we use the variable w variable times x, because x here we treat as a fixed number. Yeah. X in this representation, given f of x, we evaluate f value at x, so we fix than x value. So inside this integral, x is fixed, w is variable. W changes. Yeah. W changes. Yeah. So the Wn x is replaced by variable w times x. Yeah. So then, yeah, fl function, remember, goes to fl, right? When L goes to infinity, FL approaches original F function. So here we use the F function. Yeah. All right. Yeah. So then cosine Wn times V, Wn, we use the W variable, so cosine WV times dV. Yeah. dV, but this dW is outside. Okay? Yeah. So that delta W, the dW, we move it, yeah, outside. Yeah. Then the second term, similar. Second term, when we take the limit, similar. Yeah. So at the end, we represent the original F function using, this big integral representation. Okay? To make this big integral because it looks so complicated. This integral representation, yeah, if we look at the structure, there are two terms. There's a cosine term, sine term. Yeah. But the cosine term, it's a nested integrals. Yeah. Yeah. Two levels of integrals. Inner integral and outer integral. Yeah. It's a, double integral, right? It's a double integral. The second term, sine term, also a double integral. Okay? All right. So now we want to represent this relatively complex formula a little easier. So we introduce notation. The first notation, capital AW, we use it to represent, yeah, the single integral. Yeah, here. We want to avoid that double integral representation. So we introduce a new function, capital A function equals 1 over pi times integral of f of v times cosine wv. Okay? Then dv. Yeah. So given f function, we can calculate this expression, right? Yeah. So capital A of w can be calculated from the given f function. Yeah. Similarly, capital B function can be calculated from the given f function. After that, we have capital A function, capital B function. They are both known, so they are known functions. We can use these two functions in our final formula. So our final formula becomes f function equals integral. This time you can see the form. It's a single integral form. Yeah, because the double integral, too complicated. Yeah. So after we calculate this capital A function, capital B function, so we get a final formula, single integral, but we need to use the capital A function times cosine wx, capital B function times sine wx, adding together, take integral, but integral from 0 to infinity, okay? Not from negative infinity. Why? Because when we take summation from 1 to infinity, only half, the positive half. We don't have the negative half, right? Yeah. So that's the reason. Our integral from 0 to infinity. Yeah. We don't have the negative side. Yeah. So this f function, the final representation. So we call this formula the Fourier integral. Okay? We represent this f function. So this f function, not periodic, and it is defined on the whole real axis. Yeah. So then we can represent this function in a special integral, and we call it Fourier integral. Okay? Yeah. That's the whole story behind this Fourier integral concept. Yeah. Yeah. So here, in this class, I spent a lot of time, yeah, because this concept is very important. Yeah. So I have to explain it well, to help you understand it well, then we can go to the following steps. Following steps all established on this step, on this Fourier integral formula. Okay? Yeah. Just some special cases. Next, we need to consider several special cases of this formula. Yeah. All right, so let's move to the, some example. Dirichlet's discontinuous factor. Yeah. All right, so consider this special function. Yeah. All right. So this function, very simple. Yeah. Only takes 1 and a 0 value. Yeah. In the interval between -1 and 1, it takes value 1, and outside takes value 0. Yeah. All right. Find the Fourier integral representation of this function. Yeah. Here, this place, because this function, it is defined on the whole real axis, right? Second, we do not treat this function as a periodic function. Yeah. Although some people may argue, so we can do the periodic extension, right? The left-hand side, right-hand side, we keep duplicate, that non-zero part. Yeah. So you can do that. Yeah. But here, when you do that, you get a completely different function, right? Yeah. Here, we don't want to do the periodic extension because it's a completely different function. We just want to work on this particular function, no change. No. But after we derive the Fourier integral, we can calculate Fourier integral from this function. Yeah. So let's just do the calculation. Yeah. All right. The calculation, straightforward. Yeah. All right. So we need to, here I copy the formula. Okay. We need to calculate the capital A function, capital B function, and after that, we can represent this f function in the Fourier integral form. Yeah. All right. So capital A function, yeah. So we can, do the integral by parts. Yeah. Integration by parts. Yeah. Pretty easy. Yeah. So you get this expression. Yeah. Okay. All right. Then, capital B function. Yeah. Capital B function. 0. Yeah. Because the reason is very simple. Because the sine function is an odd function, right? The sine function is an odd function. And here you take integral on this symmetric interval, right? From -1 to 1, it's a symmetric interval. Yeah. On the symmetric interval, you take integral on the odd function, the positive half, negative half cancel out. So that's all 0. Yeah. All 0. Okay? All right. Then we can write f function. We only have the cosine part. We don't have the sine part. Yeah. Now you see the final representation. F function can be represented in this special integral form. Yeah. Yeah. When you look at the result, it's not easy to see it, right? How can you see this function can be represented in this nice integral? Yeah. It's hard to comprehend immediately. If you do not apply the Fourier integral formula, how can you get it? Right? How can you get it? Yeah. It's extremely hard to see it. Yeah. But by the Fourier integral formula, yeah, we can get it. So here, just another interesting phenomenon. So you can see we can get many unexpected results from our new tool, yeah, Fourier integral, new tool, unexpected results. Yeah. what kind of unexpected result? Yeah, so this formula already, unexpected. Then let us plug in the value to see. Yeah, because left-hand side is the original function defined here. We can see f of 0 equals 1, right? It's easy to see that f of 0 equals 1. So you plug in x equals 0 into this formula, it's correct. Yeah. So the left-hand side is 1. The right-hand side is 2 over pi integral from 0 to infinity. Cosine w times 0, it is 0. Cosine 0 is 1. So it is gone, right? Cosine part is gone. So you have sine w over w. Sine w over w. Then you take w, you take integral, you get that formula. Unexpected, right? This result. Then you do some simplification, you get a integral from 0 to infinity on the function sine w over w. It is 2 pi. Yeah, because you multiply, to that side. So it's pi over 2. Yeah, it's pi over 2. How can you see it, right? Yeah, actually this is a, very famous formula. Yeah. First, it's hard to prove. Yeah. If you want to prove it directly, it is hard to prove. How can you prove that, right? How can you calculate this integral? Yeah. How to prove? Yeah. So there are many different ways. Yeah. People can prove this formula. Yeah. Here we use the Fourier integral. It is one of the ways we can prove this nice result. Yeah, nice result. Yeah. All right, so we just use it as a simple example. Yeah, related to the Fourier integral formula. Yeah. All right. Yeah. B.4. Yeah, the special case. So let's try to finish this topic. Before the break time. Yeah. So then after the break time, we can start new topic, part C, Fourier transform. Yeah. Because this Fourier integral is a foundation for the Fourier transform. Yeah. After we understand the Fourier integral, then we can look at the Fourier transform, another big important topic we need to learn, Fourier transform. Especially for engineering. Yeah, Fourier transform, extremely important. Yeah. All right. B.4. Fourier cosine integral and Fourier sine integral. Yeah. The special cases, sine, cosine. Yeah. Related to even function, odd function. Yeah. When f is an even function, we should have this Fourier cosine integral, right? Because cosine is an even function. So we should have this Fourier cosine integral. When f function is an odd function, we should have this Fourier sine integral function. That's simple. Yeah, okay, yeah. So let's look at the, yeah. So the derivation is pretty straightforward. Yeah, derivation. Yeah, okay, all right. Yeah. So we consider two cases. Even function case and odd function case. Even function, we know the definition of even function. Yeah. F of negative x equals f of x. Yeah. Symmetric about y-axis. The graph is symmetric about y-axis. Odd function, symmetric with respect to the origin. Origin. Okay, yeah. So f of negative x equals negative f of x. Yeah. All right. Now, let us calculate the Fourier integral formula for these two types of functions and see what are the formulas. Yeah. So we expect to have a simplified version of the Fourier integral formulas. Simplified versions. Yeah. All right. Yeah. Fourier cosine integral. Yeah. Because if you look at that, f is an even function. For the for the capital A function calculation, we just keep it. Keep it. But for the capital B function, f function is even function, sine function is odd function. We know even function times odd function, still odd function. Then when we take the integral on an odd function on some symmetric interval, right? From negative infinity to positive, it's symmetric interval. The positive half, negative half can be canceled out. If cancel out, that BW function is 0. So when we write this Fourier cosine interval, the BW function is 0. So we only have the AW function. So f of x, if it's an even function, we can write it in this simple way. So much simpler than before, right? So that is, we call this Fourier cosine interval. Similarly, Fourier sine interval. This time, f is an odd function. Then when you calculate the capital A, odd function times even function, it's an odd function, right? Odd function, you take integral on a symmetric interval, cancellation, it's 0. We know. AW function. So the Fourier sine integral A function is gone, so we only have this B function term. That B function, as defined before. So that's the two special cases for the Fourier integral formulas. So pretty straightforward. Simplified version. The general version and the two simpler versions. All right. So the last step, we want to calculate a special integral. So we call it Laplace integrals. Related to the Laplace transforms. But here we calculate some special type of integral. Using the E function. We know Laplace transform, we need to use that E function. All right. Calculate the Fourier cosine and the sine integral of f function. The Fourier, think about why we can calculate Fourier sine and the Fourier cosine sine integrals of this function. So with some special, k is a special constant. K is a special constant. Because sine function, cosine function, if we can calculate Fourier cosine, Fourier sine integral, the function should be even function or odd function, right? So two cases. So here we need to make, because this original function, it's not an even function, not an odd function, right? So we need to do some special extension. Even function extension, odd function extension. Then you can make even function, odd function, right? So for example, so here I use the space here. Original function, so when we start at 0, it's 1, right? So the function value at 0 is 1, so the function, goes to infinity. So that's the shape of the positive half. Right? Then, if you want to calculate Fourier cosine integral, you need to make this function even function, right? So you need to do extension. So at the negative half, you need to flip, do, symmetric extension. Yeah. Even function, extension. Yeah. So you make this function, then you can calculate the Fourier cosine integral. Yeah. Similarly, for sine integral, yeah, this time you need to do extension in this way. Right? Yeah, in this way. Make it an odd function. Then you can do the Fourier cosine integral to represent that function. Okay? Yeah. All right. Yeah. Yeah. So here we just do the calculation. So here we assume we use the appropriate extension. Then we do the calculation. Yeah. Yeah. All right. Yeah. Yeah. So the formula, yeah, for the sine, cosine, yeah, extension. For cosine case, we need to calculate a function first. Yeah. Plug in the formula, calculate. Yeah. Yeah. A functions. Yeah. Yeah. So that function, yeah. Yeah. The result. So this is the result. Yeah. Yeah. So you can try. So can you calculate in this way? Yeah. Right. Yeah. The integration by parts. Right. Yeah. Integration by parts. Yeah. Can you get this one? Yeah. All right. Yeah. So then yeah. So here. Right. Yeah, because remember, integration by parts, then you need to evaluate from 0 to infinity, right? Yeah. Yeah. So then you get that. Yeah. All right? Yeah. So after that, then you can write. Yeah. Yeah. So here, consider when you write this function, you restrict yourself x positive axis, k positive. Okay? Yeah. So you have to do the evaluation in this special case interval. Yeah. Then you have this expression. Okay. All right. Yeah. Yeah. So that you can simplify. Yeah. So this is the Laplace integral. Yeah. So you can see this integral. It's hard to see it, right? If you do not use the Fourier cosine integral, how can you get it? Yeah. So here's the idea. So we want to get some interesting result. Yeah. Without using Fourier cosine integral, how can you see this result? Very hard, right? Yeah. But here we apply the Fourier cosine integral formula. Yeah. It's not too hard. So the main calculation is this step. This step, so you do the integration by parts. Yeah. But this step you can do together with another formula. You calculate them together, yeah, recursively. Yeah. Because when we calculate this b function, yeah, you need to calculate another related term, this time for sine. Yeah. So these two terms actually are correlated. Yeah. So when you do calculation, you consider, okay? So you can use one variable to represent the first integral. Let's say I1, okay? I1 equals the first one. Then another variable I2, that one, because when you calculate I1, when you do integration by parts, you may need to use I2. Yeah. When you calculate R2, when you do integration by parts, you may need to use I1. Okay? Then you solve a simple linear system. You can find I1, I2. Yeah. So in that way. Yeah. All right. Yeah. After that, yeah. Now, yeah, because we need to evaluate from 0 to infinity. Yeah. Then you have this. Yeah. Okay. Yeah. All right. Yeah. Right. W is fixed. Yeah. Remember. Yeah. 0 to infinity. That's V. Yeah. So V from 0 to V from infinity. Okay. W must be fixed. Yeah. So V goes to infinity. So you can see this term is 0, right? Yeah. So the infinity, that term, the whole thing is gone. Then you plug in V equals 0, E term is gone. So 0 sine term is gone. You only have cosine term. Yeah. So that's pretty easy to see it. Yeah. All right. So then you have another version to represent the same function. Yeah. Because this function, you also consider x positive, k positive. Yeah. You can see the same function, but you have two different representation. Okay? Yeah. One that's cosine way, another sine way. How about that? One sine way, one cosine way. See? Two completely different representation, but they are actually the same function. Okay? Yeah? Yeah. And it's hard to see why these two functions are the same. Hard to see. Yeah. But we derived these two formulas from the Fourier cosine integral, Fourier sine integral. Yeah? Without any problem. So you can see how powerful these formulas are. Yeah. All right. Yeah. So the final formula, that formula, non-trivial, right? Yeah. So it's, if you need to calculate the left-hand side integral directly, very hard. How can you calculate it? Right? Very hard. Yeah. Yeah. So here we apply the Fourier sine, Fourier cosine integral formulas. Yeah. So we can prove these two relatively complicated formulas. Yeah. All right, so we complete this topic, Fourier integral topic. Yeah. All right, so let's take a 10-minute break. Yeah. After the break, we will study another important topic, Fourier transform topic. Yeah. Yeah, two students joined us in the middle, so let me check their names, attendance check.
Yeah, Matthew, I'm here.
Yeah, oh, okay. Matthew, yeah, Jesus, two students, right? Yeah, Matthew, Jesus. Yeah, all right. Let me